Hi, I'm Bill Vass, a CTO at Booz Allen, and I'm here with Drew. Drew, why don't you introduce yourself?
Hi, I'm Drew Massey. I'm an AI solutions architect at Booz Allen Hamilton.
Yeah, it's great. And we're going to be talking today about Code 19 and some of the things we're doing with them as our partnership, and a little bit about how that also relates to some of the high-speed autonomy that has to happen across our mission spaces, like in the Department of Defense and other things like that. We think that, Code 19 and the crucible of motorsports is a great way to push technology in automotive world, but also across the Department of Defense and other parts of the government that require high-speed autonomy. So, Drew, why don't you tell me a little bit about what we've been doing with Code 19?
Yeah, absolutely, Bill. So what we've been doing with Code 19, we've got a couple different things under our physical AI. So one is, how do we reconstruct these environments to be both visually and physically accurate?
Yeah.
So we're working with our NVIDIA partners and Code 19 partners to both capture this aerial UAV data, as well as convert that data into a 3D visual.
So why don't you stop this and you can explain a little bit more about what we're seeing here. So this is photogrammetry data, right?
Yep. So the first thing we do with this video data is we do structure from motion. So we're doing feature matching across all the frames in the video so that we generate this point cloud, which will then be used to do the mesh reconstruction.
And then how do you define where the drones are going to fly and things like that? Are you working on autonomy there as well?
We are looking at autonomy. Right now, we're doing a lot of manual testing to see what is the optimal flying patterns, but we're looking at how we can convert that to autonomous behavior so these autonomous systems out in the field can reconstruct these environments without needing human intervention.
And of course, we're working also not just with Code 19, but NVIDIA is a big partner of Booz Allen, and we've been doing a lot with them on physical AI. So originally, I used to call it 3D AI, but it's become physical AI, but it's very much about the full physics, simulating the full physics of the real world, and then using that for autonomous training, because you can't really train unless you have the physical world, if you like. And you can do a lot of edge cases in autonomy you can't do in the real world as well. And of course, racing is an edge case. So let's talk more about what we've done here.
Yeah, absolutely, Bill. And also with the race car, it's very expensive too. So you can't crash race cars.
Yeah, that would be a bad day. Yeah.
Yep. So we're working, as you mentioned, Bill, with NVIDIA on some of the newest reconstruction technology. So we're using some of their newest methods in Gaussian splatting for these 3 environments.
Can you explain Gaussian splatting and kind of what it is?
Yeah, absolutely. So Gaussian splatting is taking that point cloud and it's doing an estimation of where it believes those Gaussians should be to fill in that space. So it's a higher fidelity visual rendering than what you would get if you were doing traditional photogrammetry, which is doing triangulation of the meshes.
Yeah. I mean, Gaussian splatting is kind of replacing photogrammetry, but photogrammetry has the advantage of being able to do a 3D point cloud rather than a viewer. Gaussian was just for viewing. How are you getting from the Gaussian 3D to a 3D point cloud?
Yeah, that's a great question. We're working with NVIDIA to use some of the latest AI techniques to do that. So some of that is neural rendering that NVIDIA has done with NERFs.
Yeah.
And there's other methods as well to take that point cloud data and reconstruct it on a mesh.
Yeah. NERFs are an important part of it. And I think there's still some evolving technology there that really needs to get smoothed out. So talk to me, how did you extract the track from the image?
Yeah, so we're using some of NVIDIA's latest tools with their VDB technology. So we're able to use segmentation methods to take this track data in this 3D environment and pull that out. What we can do with this is really interesting. We can start to apply physics properties so that the simulations can use these physics properties. So racing, the way the tire interacts with the track is very important. So this enables us to really up the physical fidelity of these simulations.
Yeah, cool. Let's keep going.
So we're also using some of NVIDIA's newest simulation technology, Isaac Sim, Omniverse, Isaac Lab. So what we're doing here is we applied those physics properties to the track. So we've got an asphalt material on the track, as well as a dirt material. So that starts to affect the dynamics of the car as it's driving over the road.
Yeah, why don't you stop it here, because this is important. So here you're doing a full synthetic environment, but you're also creating a synthetic LiDAR sensor, right?
That's right.
Yep. So as the car approaches the other car, you're going to see what it would see, not just in its cameras, but also in its LiDAR image as well.
That's right. Yeah, you can see, as you mentioned, Bill, as you pass the car here, it starts to show up in the LiDAR sensor.
Yeah, they're right there.
And what we can do with that data is start to train an opponent detection model so that the planning system is able to use that to make the optimal trajectories on the track.
And then you can also feed in all of the sensors that you can synthetically generate for the car, the tire angle of attack, the pinion, and the steering components, the brake temperatures, tire temperatures, vibration, acceleration, all of that kind of stuff that you get in the real world. You can create synthetic sensors for those, feed it into the simulation, and then run millions of miles of simulation that you just couldn't do on the track. Then you feed that into, again, as NVIDIA would say, there's a 3-computer model that they talk about, right? Whereas one computer is the synthetic environment that we see here is the training environment, which they do with Omniverse. The second computer is the AI engine computer, or the brain. And the third computer is on the car when it's in the real physical world, right? After you've trained it, you can push that out to have the car actually operate on its own. Some of it still is connected during operations, but it's got to also work disconnected as well. A car can't crash when the network goes down, right?
That's right. And the final part that we're working on with Code 19 is generating those optimal behaviors for the racing. So ultimately, racing is a competitive game. We're trying to beat other racers on the track. So what we're working on right now is using some of the latest reinforcement learning techniques and imitation learning techniques to optimize that behavior so that as the car is driving, it's making that optimal decisions. And by the way, it's doing that really fast. You only have a split second to make these decisions on track.
I think that's one of the important places, that this is a great place to test out high-speed autonomy, just like, DARPA did the Pikes Peak Challenge so that it could do high-speed autonomy, because that's what happens in the real world in a defense situation, right? Drones move at high speed, aircraft moves at high speed, ground vehicles have to move at high speed. And so there's a nice correlation between the work that we do here with Code 19 and the autonomy that we work to put on autonomous vehicles for the Department of Defense and others.
That's right. Yep.
Very exciting. Well, thanks for the demo. It's really great to see it progressing. I look forward to a lot more to come, and how this is going to be sort of the whole pipeline getting much smoother and a lot more simulation autonomy. And it'll be nice to see Code 19 win some races too.
Absolutely.
Thanks so much.
Yeah. Thank you, Bill.